So the title of the lectures is something like some topics in quantum field theory, right? And yeah, so that's what we're going to discuss, quantum field theory. So let's see, I want to cover a few things that are probably interesting or exciting, but let's see how far we can go. I will try to make the lectures a little bit self-sufficient, so I will assume that you don't know anything. No, I mean, you know something, but okay, not everything. So there's a few things that I want to focus on. One of them, because they play an extremely important role in physics, in particular in our field, in fundamental physics. This is about this is gauge redundancy, and so understanding the consequences of gauge redundancy. Then things about quantum to classical transitions, and things connected with topology, okay, and the structure of the vacuum. So, so let me start with some small introduction. Also, of course, you can stop me anytime and ask the questions. So now we are, so in our field, which is called particle physics, and it's a field that is trying to understand nature at most fundamental level, and we use certain framework for understanding nature. And this, I don't know whether to call it a framework or a method or apparatus, which we often call an effective theory, effective field theory description. Okay, and so for a particle physicist, so I'm a particle physicist. So for me, every time I think about the system, I think in terms of effective field theory. It doesn't matter what the system is. It could be a quantum field, could be a black hole, could be whatever, a human brain or whatever there is. The first thing I'm trying to understand, what is the effective description, okay? What is the effective field theory that describes the system? Now, how do we define, how do we construct an effective field theory description of something? What are the key ingredients? So the first key ingredient is to identify the correct degrees of freedom. Okay, so what are the degrees of freedom of your system? Okay. Now the degrees of freedom, the choice of degrees of freedom is not uniquely defined, and it's usually a matter of convenience. Okay, so there is but usually there is one most convenient identification of degrees of freedom. Now this identification changes is energy dependent and is length scale dependent. Okay, so for in physics there is no such thing as a simply an effective theory. It's always an effective theory defined at a given length scale. Okay, and so or the energy scale. And so when we move from one length scale to the other, often what happens is that all degrees of freedom are no longer good. They no longer represent a good description. So we have to go to new bases to change them. Okay. For instance, I don't know. You can think about infinite number of examples. Like if I think about the air in this room, if I want to describe air in this room at low energies and distances much larger, way larger than intermolecular separation, let's say, right? A good description is in terms of sound waves. So sound waves are good degrees of freedom, okay? But if I want to describe, if I change the length scale of my description, if I go to the distances much shorter than the intermolecular distance, then the sound waves are no longer good degrees of freedom, okay? So description in terms of sound waves breaks down, okay? It's not a question of being wrong or right. It simply breaks down and must be replaced by something more powerful, more appropriate at those length scale. Now this transition from one description to the other, when we move from large distances to short distances, we often call ultraviolet completion of the theory. Okay. So another famous example you can think about is a theory of strong interactions, right? So at large distances, we can describe it in terms of chiral Lagrangians, which is effectively a theory of pions and Nabu-Goldstone boson type degrees of freedom. But there is but at the distances shorter than the length scale, which is QCD length, approximately 10 to the minus 14 centimeters, they are no longer good degrees of freedom. So we have to change them, and we have to go to a new description in terms of quarks and gluons, and so on. Okay, so all the time there is we constantly try to identify degrees of freedom. So therefore, if I want to in the zero approximation, if I want to describe any phenomenon of nature, I have to identify good degrees of freedom. Okay, now the question is, how do I identify good degrees of freedom? What does it mean? Okay, so what are the requirements that these degrees of freedom should satisfy? Okay, now first thing is, so first of all, degrees of freedom for a particle physicist, there is a convenient description to describe degrees of freedom as quantum oscillators. Okay, so we have some operator that we treat them as creation and annihilation operators. They satisfy certain commutation relations, as you know very well. Okay, let's say Ij. And let's say A is commute. Okay, so they're quantum oscillators. Now these quantum oscillators, they act as creation annihilation operators. They act on a vacuum, okay, and they create what you call what for you would be a good degree of freedom. Okay, so let's say act on a vacuum state, and I create some one particle state. Okay. So now the question is, there are several questions. First is, how should I identify these degrees of freedom? What are the minimal requirements that they should satisfy? And secondly, how should I label them? Okay, what is the label? Now, the first thing is that usually what we call the most convenient degrees of freedom are the ones that are interacting weakly. Okay, what does it mean? It means that, okay, you identify these degrees of freedom, and you will write down some effective Hamiltonian for these degrees of freedom. Okay. Now this Hamiltonian contains some leading order terms, right? And some off-diagonal components, which describes higher order interactions between these oscillators that destroy some particles, create other particles, and so on. Okay, like in Fermi theory, for instance, right? You destroy a neutron, you create proton and leptons, and so on, right? Now, so this Hamiltonian governs the time evolution of your state. Okay, so you have a certain Hilbert space. In this Hilbert space, you have a state, and there is some time evolution governed by this Hamiltonian. And so this is happening in some appropriate part of the Hilbert space. Now, appropriate part of the Hilbert space, I mean, this is the part of the Hilbert space that is relevant for the problem that you are trying to solve at that moment, at that time. Okay, all right. I don't know if I'm interested. Let's say E plus E minus scattering at LH at whatever collider. I'm interested in a very limited part of the Hilbert space. I'm not interested in the evolution of the universe starting from the Planck epoch, right? and so on. So there is some relevant part of the Hilbert space. And so what you want is that these degrees of freedom are weakly interacting as far as this relevant part of the Hilbert space is concerned. Okay, so in other words, you want to make sure that the off-diagonal terms in the Hamiltonian are less important than the diagonal terms. Okay. Now, if they are not, this means that your choice of degrees of freedom is not terribly convenient. So you have to rediagonalize your Hamiltonian and choose the basis in which this will happen. Okay. Is this clear? Any questions about this? Okay, so therefore, the first requirement is that I will impose on these degrees of freedom is that they satisfy this condition, so they are weakly interacting. Okay. By the way, if you think about the examples that I gave, for instance, if I think about pions, that's precisely what happens. So what happens is that the need for the change of the degrees of freedom and going to a different description always happens, is always accompanied by these old degrees of freedom becoming strongly interacting in that domain. Okay, so for instance, this what happens with pions. If I want to insist and describe nature in terms of pions above the scale of the chiral Lagrangian, above the QCD scale, above I mean in the energies, or distance is shorter, I will discover that pions no longer satisfy this condition. They are strongly interacting. Okay, so and therefore that's why I have to find new degrees of freedom which will be weakly interacting, and those are quarks and gluons, for instance. Okay. All right. So somehow usually when we have to change degrees of freedom, nature has a way to tell us about that. Okay. So there is. Theory tells us when we need to change degrees of freedom. The theory will always signal with some strong coupling phenomena or some singularity and this kind of stuff. Okay. Okay. So then, this is first thing that I will try to obey this rule of the game. And the second question is about the label. Okay. How should I label these degrees of freedom? Okay, what are the good labels? Now, good labels are, of course, the ones that are most convenient, right? Now, since in particle physics description of nature, we often use the so-called S matrix setup, right? So we always think in terms of an asymptotic observer, an S matrix observer. Okay, so I should not go down to this red line, or that's the idea? Yeah. I should not. Okay. Yeah. So the S matrix description means that you can define some in states, and then there is some interaction happening. Then there are out states. Okay, and you have an observer, Alice, let's say, who is an asymptotic observer, and she can control in states and out states. So now, in states and out states we normally treat as non-interacting particles, defined which represent excitations on top of the vacuum of your theory. Okay, so therefore, it's very important what is the vacuum of your theory. The vacuum of your theory, of course, is this, that in terms of your degrees of freedom, okay, the distraction operators are annihilated. Okay, so this is normally we define as a state without particles. These degrees of freedom we often call particles, right? Now, then the question is, what are the symmetries of your vacuum? Okay. Now, most of the time I will try to be in the vacuum, which we like usually. That's Minkowski vacuum. Okay. And Minkowski vacuum has certain symmetries. In particular, so a Poincare symmetry, right? Okay. And so correspondingly, it's useful to label these degrees of freedom by the symmetries of the vacuum. Okay. Of course, this is also a symmetry of your Hamiltonian. Okay, but as you know very well, it may happen that your Hamiltonian has a symmetry which is not respected by the vacuum. In that case, we have spontaneous breaking of symmetry. It still continues to be useful in many cases, again, to use even spontaneously broken symmetries as a label. Okay, so it's not that one symmetry is spontaneously broken, you can throw it out. No, it's again useful. But here, in this case, I'm talking about symmetries which I assume that they are not broken. In Minkowski, of course, they are not broken. Yeah, Poincare symmetry. Okay. Now, Poincare symmetry has certain Casimir operators. Okay. So, which are what? How many Casimirs are there in Poincare group? Who remembers? Yeah. 10? No, 10 is too much. Casimirs, I'm asking. Casimir operators. 2, yes. Yeah, that's the mass and the spin, right? So that's why we label elementary particles by masses and spins. That's why they are good labels, because they are Casimirs of Poincare group, okay? Commuting with all the generators of the group. So that's why, for instance, masses and spin are good labels of elementary particles, okay? Of course, you can have also plenty of internal symmetries, which again are good labels for elementary particles. So basically, the point is that it's useful to label these degrees of freedom according to their symmetry transformations, okay, with respect to the symmetries of your theory and symmetries of your vacuum. Okay. Okay. Any questions so far? Now, the question is, okay, fantastic. So we now want to describe nature in terms of this. And then we have to build field theories, okay, of different masses and different spins, okay? And when we start doing this, a certain concept emerges which is looks a little bit unusual, okay? This is the concept of gauge redundancy. So what we are observing is that theories of spin higher than 1/2, so 1 and higher, but even that is not true. Even for spin 0, you can have a description, okay, which is similar. So these descriptions, they exhibit what we call gauge redundancy, okay? Now, and of course, the moment you encounter a redundancy, the question is this just simply an artifact that we are not smart enough to find correct degrees of freedom, or there is something fundamental about the redundancy, okay? Now, this gauge redundancy imposes powerful constraints on the types of the theories that are consistent, okay? And what we are observing is that higher you go in spin, tougher become these constraints, okay? Now, let's discuss a few things about gauge redundancy, okay? So the gauge redundancy will play a very important role in what we want to discuss, okay? And so let me introduce few concepts and remind you, etc., etc. Now, the first thing I want to make it clear that we understand what we are talking about, okay? Right? Now, the simplest prototype theory that we usually discuss in the textbooks itself, which exhibits gauge redundancy, is Maxwell's electrodynamics, right? Okay. So let's take this as a starting point, the Maxwell's electrodynamics. So it describes a vector potential, okay, 4 vector, A mu, right? And we write Lagrangian of this Maxwell theory, okay, in terms of a field strength, right? So we have a So in the language of forms, which I will try to make indices explicit and discuss in the explicit language, but in the language of forms, this is a one form. Okay, so vector potential, Maxwell vector potential is about one form. So, and we write this Lagrangian in terms of the field strength. Where J mu is a source that, okay, and we have to specify at some point, okay? So this describes a Maxwell field, a vector field, okay, coupled to a source, all right? And now let's investigate this theory a little bit to prepare the basis for things that, okay, will also be gauge redundant and try to understand different aspects to warm up. So, okay, so we do, let's say, we write down the equation of motion. And this is the famous Maxwell equation, okay? Now, this theory is gauge redundant, right? So it exhibits redundancy with respect to a transformation of a vector potential. You can shift it by an arbitrary derivative, okay? So the field strength is not changing under this transformation. Okay, very good. So now the question is, why am I requiring this type of construction? Okay, so why am I because, of course, one thing is nature. So sure, this describes electromagnetic interaction extremely well. But suppose I don't have this phenomenological information, and I want to construct a theory of a particle, of a quantum field that would describe some particles of spin 1, okay, massless particles of spin 1. Why should I make this choice, okay, of this form? Now, of course, you can say, oh, if you don't do this, then we'll so-called, sometimes people say, if we don't do this, then we break gauge symmetry, okay? Now, that statement is not a correct statement. We will not break gauge symmetry if we don't do that. Something different will happen, as we'll see, okay? But even if we break gauge symmetry, who cares? You can ask me, why do I care about gauge symmetry? I want to construct a theory of spin 1. So, right? Okay, what I want to know, whatever theories are there. Okay, if there is a theory which is gauge non-redundant, even better. What's the problem? Okay, let's see, right? Okay, so now in order to understand why gauge redundancy is fundamental, we need to first understand the question of degrees of freedom, because it's intertwined with the question of degrees of freedom. Okay, what are the degrees of freedom of this theory? Okay, now degrees of freedom of this theory you know extremely well, right? How many degrees of freedom are there? But let's remind ourselves how we proceed. Right? We say, okay, once I choose my theory in this way, there is a gauge redundancy. This gauge redundancy I can use to kill some degrees of freedom, okay, right? So I would say, okay, it's a 4-vector. I would have some 4 independent functions, but I can impose a condition, okay, by choosing the gauge to kill some of these degrees of freedom. Now, one convenient choice is to choose the vector potential to be divergence free, okay? Why? Because if I choose in this form, then this equation, which doesn't look very nice, gets a form which is nicely invertible, okay? Laplacian, the D'Alembertian operator, okay? In this gauge. Now, how do I know that I can do this? Okay, how do I know that I can choose this gauge? Well, I know because, let's say I start with a field for which this is not true. All right? So let's say I have my starting field has this non-zero. All right? And then I go to a new field, a mu, by shifting the old one by some alpha. And now I impose that new one satisfies this condition, right? If I impose this condition on a new one to be 0, this will look like an equation for alpha with a source, right? So this simply will tell me that alpha as a scalar should satisfy equation with a source which is divergence of my old A mu. And this equation always has a solution. Okay, so I can always find corresponding alpha to kill the divergence of the vector potential. Okay? Okay, very good. Then the equation acquires a simple form, and we cannot go beyond the red line. So okay, so this kills 1 degree of freedom. Okay, so we have eliminated 1 degree of freedom, and we are left with 3, right? But there is a residual gauge redundancy, okay? Because we can shift further, we can correct the shift by additional alpha prime, as long as alpha prime satisfies the, as long as the divergence is 0, okay? Then we are not upsetting this condition, right? And so we are not upsetting this condition. Now we can use this additional shift to eliminate 1 more degree of freedom, but on shell. Okay, so now we are eliminating 1 more on shell. So one we eliminated whatsoever, okay? And the second one we are eliminating on shell. And we are left with 2, okay? So therefore, we have 4 minus 2, and we have 2. So there are, therefore, 2 propagating degrees of freedom, okay? In this theory. Okay, so are we, any questions? Okay, very good, right? All right, so now we can come back to a question. Why this form? Okay? Because the structure of these objects by up to partial integration is that, so for a vector I could have written 2 types of kinetic terms, right? So there is one which is with the contraction, and there is another one with a contraction of divergence, right? And so this gives me up to a coefficient, which okay, overall coefficient. But the coefficients are tuned among them, right? So it must be exactly this minus this, okay, right? This form. And the question is why? Of course, this is the one that gives me this gauge redundancy, right? But what would happen if I would not impose this condition? Because let's say I don't care about gauge redundancy, right? So what would happen? Okay, everybody understands the question, right? Okay, so let's try to change the theory, okay, therefore, and do something like this. So instead, let's consider a new theory in which I slightly disbalance these two coefficients. So let's say I add an additional, let's say I add some epsilon, or let's call it psi. Okay. Now, I've changed the theory, okay? And so I want to understand, so when I'm changing the theory, okay, one of the things that I should be interested in, okay, changing theory means we deform the theory. Sometimes we use this language, deformation of the theory. And when I deform a theory, one of the things I should be interested in is the limit. Whether deformation of the theory gives me something continuous, okay, or there is a discontinuity in the deformation of the theory, okay? All right? So in other words, we need to understand the first thing you have to worry about whenever you deform your theory is whether the limit is smooth when you take deformation to 0, okay? So let's try to figure this out, okay? So this is psi, sorry for my psi, okay? And so we want to understand if the limit is smooth, first thing, okay? And secondly, we want to understand what this theory with psi non-zero describe. What does it describe, okay? Now, so important thing is to, a lot of problems in physics, right? A lot of mistakes we make because we use notation. We don't care about notations. Sometimes we should care about notations, right? And so it is very important not to confuse ourselves to change the notation for A in a theory with psi. Just to remember that this is a new field, okay? Because nobody guaranteed me that the limit is smooth. Since I have no guarantee a priori that the limit was smooth, I am obliged to change, to call this A a different symbol, okay? To denote it by a different symbol. Yes? Yeah. No, this f mu nu, so yeah, that's what I said. So let's define this f mu nu once and forever to be this. That's it. So then I said, then with this definition, so Maxwell would be a theory with psi equals 0, and now I'm deforming my theory and putting some psi non-zero. Okay?
But if you know what f mu nu is, because it's defined over here, you can't multiply them together and then say,
no, I don't understand what you mean. So this is just, so without this term, this is just standard Maxwell. Okay? So with where I have defined f mu nu as it's written there. That's
but then suddenly we have something new, and the new
yeah.
comes from the line above, right? Comes from the line above, f mu nu, right?
No. This is not coming from line above. I just said that. No. Yeah. Okay. Let me explain again. No. Thank you for bringing it. So now what I said is that f mu nu, if I view f mu nu bottom up, right? Okay. So let's say I don't read textbooks and I want to reinvent myself on Maxwell theory, right? Or whatever, right? If you tell me to construct a theory of a vector, all right, then I would say, okay, let's see. First, let's write down a kinetic term. And I would say, okay, there are two choices. I would write kinetic term like that and kinetic term like this. Okay. So in other words, I would say that I would write in a theory, in which I would say with some coefficient alpha, or let's call it some coefficient A. I don't know. Let's call it some coefficient C1. Okay. Okay, I would say, okay, there is this possibility, okay, and with some coefficient C2, there is another possibility. Up to partial integration. Okay, up to partial integration, these are the two kinetic terms that I could have written down. That's all I'm doing. Now, in Maxwell, we chose a very special point where these C1 and C2 are correlated in an extremely special way, right? And that's Maxwell. That's what happens, right? Now I want to keep generic C1 and C2. So I'm writing my theory. So this I can always write as Maxwell plus something else. That's all I'm doing. So I'm trying to write the theory as a deformation of Maxwell. Okay? Why? It's just a matter of convenience, because in Maxwell we understood, at least we think that we understood, we understood how many degrees of freedom are there and what is the structure, right? And so it's useful to go from the theory that you understand, usually, right? That's what I'm doing. Okay, so we have now this theory. Now let's investigate this theory. Now, as I said, it's very important to put tilde, to change the notation. Okay, I will change notation by putting tilde here. Okay, which means that now this f mu nu is also a function of tilde. Okay, and so on. So everything is depends on this tilde. This is, as I said, this is a necessity. Since the moment I wrote here psi, A tilde became a new object, and even the limit, I'm not guaranteed that even the limit is smooth. Yes.
Well, I'm confused. So the F should not be F tilde, or?
Yeah, F should be F from the tilde. Yeah. So this F now that I'm writing here, I don't want to put tilde because usually people denote with F tilde a dual field strength. You see the problem of notations, but but remember that this F is out of this tilde also. Okay? If you can offer better notations, I can go with them. Yeah.
When you take C to 0 its limit, will A become A tilde just become A?
No, will not. That's the whole point. We want to understand whether that's what is happening. We don't know. Nobody guaranteed us. You see, that's the thing about quantum field theories, that quantum field theories can often trick us. We think that because Lagrangian becomes a old Lagrangian, but this doesn't mean that the theory becomes an old theory. And this is extremely important. In quantum field theories, we have discontinuities all around, and discontinuities go with gauge redundancy. This is the fact of nature, and that's precisely I want to explain. Okay, so that's why I don't want to call this something else. I want to call it tilde or, oh sorry, this is now this is a different thing. Yeah. Okay. Okay, so now we have a theory which depends on new vector potential, which I call A tilde. Okay, that's it, right? I mean, we can call it B if you want, but all right. But this way is better, still to call it A. Okay, so now, of course, now you ask someone to study this theory, or you study it yourself. I don't know if you have nothing else to do. So then and this person, okay, first thing to understand about theory is to stare at the equation, okay, and then we notice that of course this theory no longer has gauge redundancy in A tilde, okay. So obviously there is no gauge redundancy in A tilde. Okay, so this means that we cannot use gauge redundancy to kill degrees of freedom in A tilde. Okay, so we cannot do this trick, okay, of gauge choice. So we have to investigate the theory as it is. All right. So then theory. Now with tilde we have and okay, we have a source, or we may or may not put the source. Okay, so one thing I want to remind you, that was the case in Maxwell. Now in Maxwell, notice the following, that in Maxwell, if I take divergence of this equation, right, since divergence of f mu vanishes because it's antisymmetric, okay, so if I take divergence of this equation, the left-hand side vanishes, and so the right-hand side obviously of course also should vanish. And this would give me the condition that the source is conserved. So in other words, you see, in Maxwell, the conservation of the source is a necessity. It's a must. Okay. Just follows from the equation of motion. Okay, it's clear for everybody, right? Okay. Now, here. Oh, psi, yes. I missed the most important thing. Yeah, psi, sorry. Yeah. Okay, so now here, in principle, the source doesn't have to be conserved, strictly speaking, okay, right? Because of this term, okay? So instead, I will get some constraint when I take divergence of the equation. I will get a constraint which will look like something like this, that psi box acting on d mu A tilde is the divergence of the source. And so in principle you can introduce a source which has divergence, okay, which is not conserved, and this source will act like a source for A tilde, okay, for the divergence part of A tilde. In other words, what happens, right? So here the divergence of A was unphysical, so it was a gauge degree of freedom, which we could set it to 0 by gauge choice. Okay? Now here, divergence of A tilde is not unphysical, so it became alive. Okay? We can no longer set it to 0 by gauge choice, so it became alive. Now, with or without the source, that's up to you. You can introduce sources in your theory that are not conserved, then they will source this equation. If they are conserved, this equation will look like a free equation, but it still will be an equation. Okay? So this is one thing that we notice, right? Now the other thing is that since we can no longer use this gauge redundancy, all these degrees of freedom that were gauge degrees of freedom, okay, so we are unphysical in that sense that they were gauge degrees of freedom, in A tilde they are alive, okay, all right, which means that A tilde I can imagine writing as certain part that contains those degrees of freedom that were left untouched by gauge redundancy in A, and that I can expect be pretty sure that when I take psi going to 0 limit, this part of A tilde will go to the previous A. But on top of that, there is something else, which is a longitudinal part of A tilde. And I can write it as a derivative of some scalar phi. Okay? Now, you may naively think that phi, because it's a scalar, it propagates 1 degree of freedom. But you have to be extremely careful, because whether phi propagates 1 degree of freedom or many depends on the equation of motion of phi. Okay? And now we can see immediately what is the problem in this theory. Now, if I stare at this equation, for instance, okay, or even at the starting Lagrangian, beginning Lagrangian, what happens is that phi, if I think of how phi enters in the original Lagrangian through the divergence, this term gives box phi square, okay, part. So in other words, phi is a field which has high derivative kinetic term. Okay. Now you probably heard many times that one of the biggest disasters that could happen with quantum field theory is to have fields with high order time derivatives. Okay. Now such degrees. So what does it mean when I have high order time derivatives? This means that in reality phi propagates more than 1 degree of freedom. Okay. Because there are more derivatives entering in the equation. And moreover, as you heard many times, these type of fields, they are sick in the sense that we call them ghosts pretty often. They are sick in the sense that we cannot attribute them both the positive norm and positive energy. So we can attribute them positive norm, but then their energy will be negative. Now, these will be particles with negative energy, and particle with a negative energy is a disaster, right? Why? Because a theory which contains a particle which can have a negative energy cannot even be has a 0 lifetime, for instance. Okay, it cannot even have a vacuum. Why? Because in normal Maxwell theory, vacuum is stable. Okay, why? Because I cannot produce photons out of the vacuum by conservation of energy, because photons carry positive energy, okay, they carry momentum, and I cannot produce photons out of the vacuum. For instance, momentum I could satisfy, okay, I could produce photon flying in that direction and photon in the opposite direction, okay, so I could start with 0 momentum vacuum and end up with 0 momentum 2 photon state, but I cannot satisfy conservation of energy. Since photons carry positive energy, so I cannot produce them out of the vacuum. Okay, so that's why our vacuum is stable. That's why we exist, by the way. Okay. Now, in a theory in which a particle can carry negative energy, it's end of the story. Why? Because you can produce such particles out of nothing. Right? If I have a photon with negative energy, I can always produce photon with negative energy flying in that direction and photon with positive energy flying in the opposite direction. Okay? And the phase space for such processes, by the way, you can do this exercise. Probably you have done it, but I don't know. You can do it. The phase space for such processes is infinite. Okay. So okay, this is the standard problem. Okay, with high derivative theories that and with the ghost degrees of freedom that come from these high derivatives. Now, don't confuse this ghost with Fadeev-Popov ghost and this type of stuff. Okay, this ghost will not be gauge artifact. That's the whole point. Okay, this will be a ghost which cannot be eliminated by gauge redundancy because you have sacrificed the gauge redundancy of A tilde. Okay. Okay. Any questions so far? Yeah.
So even in simple Maxwell equation, unless you set that particular gauge d mu a mu equals 0, you still have that ghost term.
No. When you have a gauge freedom, this means that this degree of freedom is unphysical. In other words, you can have a slogan that the only way to, the only possibility to have ghosts in a theory if these ghosts are gauge degrees of freedom. If the ghosts are gauge artifacts, then this means that they are simply not there. Okay, then you are it's just a redundancy. It's not a physical degree of freedom. So that's what is happening in Maxwell, and that's what stops happening the moment you deform Maxwell. For instance, like this. Okay. All right. Yes.
So for me, it's not completely clear why you were able to write the last iteration in the middle board because you were saying from the beginning, in the middle blackboard, because you were saying from the beginning that it was not clear if you could write A tilde as A.
No, I said that this is not, don't think of it as A of Maxwell. Of course, it's not A of Maxwell because theory is deformed. No, I said this is A, okay, if you want, call it A of psi. This is part that could smoothly go when I take the limit psi going to 0 into Maxwell. Okay? These are 2 degrees of freedom of photon, standard polarizations of photon, 2 polarizations of photon. Okay? In the psi going to 0 limit. Okay? Sorry about notations, but you see the problem with notations. In other words, A mu of psi, this A mu of psi, this smoothly goes to A mu, but psi goes to 0. So thanks for asking this because probably it clarifies. Okay, is there anything else? Yeah.
Why does a higher derivative kinetic term imply more derivative?
We can discuss this. This will take us to defocus a little bit. That's why I told you. So for instance, you can do this exercise. Take a theory with the kinetic term. I don't know. You can play around. For instance, take a theory of this sort, some coefficient C here, that satisfies this equation. Okay, right? And you can see that this theory. Okay, so naively would think that this theory. Okay, this theory is a theory of a scalar which propagates 1 degree of freedom. Now, with a Green's function, which would look like inverse of this, right? But actually, you can prove very easily. Let me not waste. Let me not use this time for that. That this Green's function, in fact, is a combination of is a linear superposition of 2 Green's functions. Okay, one has a pole at C, another one has pole at 0. Okay, but their signs must be different. Okay, so this means that you will have this. Sorry, you will have this A of box. Again, A. I don't know. This is different A, of course. And B of box plus C, and one of them, they cannot be both positive. Okay, so in other words, the high derivative, and so you know that, for instance, we have this spectral representation of the propagator, right? So the spectral, you can think in terms of spectral representation of propagator. You may think that you have a 1 degree of freedom with high order equation of motion. But in reality, this 1 degree of freedom with high order equation of motion represents many degrees of freedom. The problem is that it's impossible to have all these degrees of freedom to be to have a positive kinetic term. Okay, so some of them should have negative, and this is the problem. Now, since you asked, let me comment a little bit. Now, if you read in the literature, okay, there are papers in which people nevertheless are working with this high derivative theories. Now, so now in some cases this is legitimate. Now, this is legitimate in the following case. If this high derivative, you understand it as a low energy expansion of an infinite series of derivatives. Okay? So if you have infinite series of derivatives, which at the end of the day resum into something non-pathological, then, okay, you can have an effectively high derivative interaction at low energies. This is the case when it's okay to work with it, but even then you have to be extremely careful how to work with it. Okay? Now, sometimes people say that that if ghost pole, for instance, if I push this ghost pole C to infinity, then I should not worry about it. Now, I don't think that's true. That's correct. Because you see, it again comes from the same folklore, the same story about our intuition about particles. Now, for instance, a W boson at low energies decouples. Okay, so at low energies, it's very hard to excite W boson if the energy my process is low, and therefore the interaction coming from the W boson at low energies is suppressed. Now, W boson is a healthy particle. It carries positive energy. Okay, you cannot apply the same intuition when you are dealing with a disaster, which has even not on the notion of normal energy. So if you have an object with negative energy, you cannot say that if object with negative energy has huge pole, therefore it's harmless. No, because it never decouples. The objects of if elephant has a negative energy, you can produce it out of the vacuum, no problem. Okay, right? And this is the thing. So you should be extremely careful. The fact that something has a pole at very high value doesn't guarantee that this object is harmless at low energies, because it's not a normal particle, it's a ghost, and that was the problem to start with this object. Okay, so that's the thing. All right. Okay, so now there is one more. Okay, we'll never finish. When
you write down a twiddle, that you can decompose it into a part with that is just a new side. Well,
that you can always do. Any vector you can decompose in longitudinal part, which is derivative of something, and then the transverse part. That you can always do. The question is whether this longitudinal part is physical or unphysical, and whether it's a trouble or not. And here it's a trouble. Okay. Now, let's again. With this will partially continue your question. Let's ask this. Okay, we need some space, right? Now, however, now this discussion also reveals something pretty interesting and important, that actually the original, so if I think mentally, you see, it's a little bit hard to think about deformation of theory that makes no sense, but let's try to think about it, right? Because I just proved you that if I deform a theory, I go in something not very pleasant. But still, let's think about it, okay, as a deformation of Maxwell. So if I think of it as deformation of Maxwell, what are we learning? Okay, so in Maxwell, I had this A mu. And when I deformed Maxwell slightly with psi, I deform A mu to something which I call A mu psi, okay? And theory discontinuously acquires another part. Okay, this is the difference. The difference is that this person was non-existent in Maxwell, was unphysical. And in this theory, deformed theory became physical. Okay? This is the discontinuity. Discontinuity is hiding in the longitudinal part. Now the statement number 2 is that this psi now restores gauge redundancy that you thought you lost in Maxwell. Right? Because why? Because obviously there is a gauge redundancy under which is similar to Maxwell, right? And phi, written in this way, simply shifts by alpha, right? In other words, it's true that there is no gauge redundancy in A tilde. So A tilde is not shifting under any gauge redundancy. But A tilde is no longer the same field that was in Maxwell. The field of Maxwell became a component of A tilde. And it acquired a partner which maintains gauge redundancy, continues to maintain exactly the same gauge redundancy as it was in Maxwell. Okay? Now, this is extremely important to understand. This field is sometimes called a Stuckelberg field. Okay? So let's try to summarize what happened. So what happened is that we tried to deform a theory in such a way in order to eliminate original gauge redundancy. And actually, we didn't succeed. We could not eliminate original gauge redundancy. What happened is that a gauge parameter of original gauge redundancy became a field which continues to maintain the same gauge redundancy in a deformed theory. The problematic part is that this field is not healthy. So the problem is not gauge redundancy. The problem is who maintains it. And in this case, it is maintained by a pathological field. And this is the problem. Okay? Yeah. No, this you cannot associate with anything because this theory, as we just saw, it makes no sense, right? So therefore, this theory is simply a theory of I don't even know what to call it because it's a non-existent theory. Okay? But we go now to massive photon. So massive photon is an example of a theory where this gauge degree of freedom becomes physical, but it's healthy. That's an example of a theory which is a healthy theory. Absolutely, yes. That's absolutely correct. Okay. Now let's go to that example. So in other words, you should not have an impression that every time I try to deform theory by trying to eliminate gauge redundancy, the field of Stuckelberg field that enters this theory is always pathological. No, there are examples when the Stuckelberg field is healthy, and that's the example of a precisely deformation of a theory by a mass term. Okay. So therefore, let's deform our Lagrangian by adding a mass term for a photon. Okay, so now again, I have to do the same thing. I have to put tilde here because this is a deformed theory. And now we are deforming it by a mass term. Okay? And let's do the same procedure. Let's investigate this theory. How many degrees of freedom are there? So again, we write down the equation of motion. Let's assume that source is conserved if you want for simplicity. Because source may be conserved because of its own dynamics. Whether source is conserved or not, that depends on the dynamics of the source itself. Okay, so for example, electromagnetic current in the standard model, right, is conserved because of its own dynamics, because there is a global symmetry of charge conservation, right, and so on. So therefore, this is up to us. Now let's investigate this theory. Let's see how many degrees of freedom does it propagate. Okay. We take divergence and we get, so this, by the way, this Lagrangian is a so-called Proca Lagrangian, okay? So Proca version of a Lagrangian. So we get a constraint that the divergence of A tilde is related with the divergence of the source. Of course, if source is conserved, then simply divergence is 0. Okay, we can entertain this possibility. If source is not conserved, okay, right, non-conservation should be controlled by the mass, as you can see, because this, as you see, the right-hand side is singular when mass goes to 0. So therefore, non-conservation should also somehow smoothly go to 0 when we take mass to 0 limit. But okay, let's set for a moment this to be 0. It doesn't matter. Okay, so then we have now the condition that we had as a gauge choice. Okay, I erased it for the Maxwell, right? Now appears as simply as a constraint. Now this is a constraint because this is simply a constraint on a field. Okay, so it's called Procca constraint. And this means that there are 3 degrees of freedom left. There are 3 degrees of freedom left. And that's it. Okay, so there are 3 degrees of freedom. So now now we can write exactly in the same form this object. So okay, I assume here that there is m mass, but okay, I will just will not carry it around. And phi, okay. And phi now is healthy. It has a healthy kinetic term, and so no pathologies in phi. It's a longitudinal photon degree of freedom. So in this case, again, of course there is gauge redundancy. This exactly the same gauge redundancy, right, remains. Everything is fine. So what happened is that we deformed a theory by putting a mass. Deformation is again discontinuous, okay, because a new degree of freedom appears. So the theory that propagated 2 degrees of freedom goes to a theory which propagates 3 degrees of freedom. Now this 3, of course, is 2 plus 1. This equation is a bit non-trivial because this tells you that what happened is that 2 polarizations of photon, they acquired a longitudinal polarization and they became a massive photon. Okay, so this is a precursor of Higgs effect. In certain sense, this is the part of the mass generation is identical to the Higgs effect. So the Stuckelberg field effectively is a Goldstone boson that was eaten up by a photon. Okay. Okay, so now let's see what are the problems in this theory, if any. All right. Okay, first let's see what are the problems. Secondly, let's see what's the relation between this way of generating a photon mass and the Higgs effect. Okay. Now let me just tell you in advance that as far as generation of the mass of the photon is concerned, there is no difference between this and the Higgs effect. In other words, there is only one theory of massive photon in nature. That theory is theory at low energy. It always looks like theory of Procca, okay, and it propagates 3 degrees of freedom. It doesn't matter whether you are coming from the Higgs or you are coming from whoever, okay. This is always the case. Now the Higgs effect gives us an ultraviolet completion of this theory, okay, but it's not adding anything to the fact of the generation of the mass, okay. So the mass is simply coming from the moment you wrote mass for a photon, the moment you write down a mass, you introduce by hand, not by hand, I mean of course by hand, but you automatically introduce a new degree of freedom. It's absolutely impossible to have photon mass without this accompanying new degree of freedom. So the moment you write it, it's there, okay? So that's why it's important, because in other words, this Stuckelberg, sometimes people refer to the Stuckelberg as a Stuckelberg trick, okay? It's not a terribly good name because, you see, there is no trick here. I mean, this Stuckelberg field is there. You can write it explicitly or not. That's up to you, okay? So you can work with A tilde, or you can work with this, the composition of A tilde, This will not change the fact of physics that there is a new degree of freedom, and this degree of freedom maintains old gauge redundancy. Old, I mean the gauge redundancy of Maxwell. Okay? Okay, so now let's see what are the issues here that we have to deal with. Now, first of all, if I want to use this form in the Lagrangian, right, we see the following, that the mass term, right, so the mass term, this mass term, now the mass term becomes a kinetic term for the Stuckelberg field, and this is always true. The kinetic term of the Stuckelberg field is always coming from the mass term of the field that is eating up the Stuckelberg. Okay. Now, so the kinetic, so therefore, as I wrote it, phi here, phi is not canonically normalized because the kinetic term, so phi is dimensionless because of dimensionality of A mu, right? Canonical dimensionality of A mu is 1, right? And so phi is dimensionless, so therefore it's not canonically normalized. In order to canonically normalize phi, to go into the language of canonically normalized phi, I have to divide phi by m. All right, so now if I divide phi by m, then this will give me a standard kinetic term for phi, and then then it will be canonically normalized. Okay. Now, if we write theory in this form, okay, I cannot go below this red line. We can see immediately what happens in the limit, right? So we have 1/2, right? If I expand this term now, right, then we have a mixing between A mu and phi. And then we have, okay. Now, so now phi is canonically normalized. Okay, so there is a mass term. So there is a mixing between the photon and the Stuckelberg, or photon and its longitudinal, two polarizations and the longitudinal one, okay, of a photon. So this term gives me, in the language of Feynman diagram, I have transition between A mu and phi, okay. Okay, through n momentum, right? And moreover, if I take the limit m going to 0, what happens with the theory? The theory simply, so the two simply disintegrate. They decouple from each other. And the theory, the limit m going to 0 of the theory is simply Maxwell and the massless scalar, and that's it. Okay, so the scalar just decouples from the vector part, and of course you see that there is a discontinuity because the taking limit of a massive theory when m goes to 0 is not giving me back the theory of a massless photon. Okay, it gives me additional degree of freedom. Now, okay, very good. So now, let's see what is the problem in this. What are the potential problems here? Okay, and it's illustrative to see that now free theory. So as long as theory only couples to external sources, and as long as these sources are either conserved or at least conserved in the limit when m goes to 0, okay, there is no problem in this theory. Okay, you can take the limit. So you can smoothly take the limit mass going to 0. The issues come up, very interesting ones, when we allow some interactions in the theory. Okay. For example, right? So you can say, okay, let me now take this original Lagrangian and add some interaction. Okay, so let me call it some gamma. A mu tilde squared, okay? Right, so I take some quartic interaction of between the massive photons. So this quartic interaction describes 4-point interaction between massive photons. And naively it looks like there is nothing wrong with it, right? Because, okay, what's wrong with it? It's not, for sure this term maintains exactly the same gauge redundancy as we already have. It's not changing anything in terms of gauge redundancy. Now the coefficient in front, what's the dimensionality of the coefficient in front? So there is a four-point coupling between 4 bosons, 4 canonically normalized bosons. So what's the dimensionality of gamma? Dimensionless, right? So naively it even looks like that it's dimensionless. Okay, so it's a very nice dimensionless coupling. Okay, but okay, the things are not so simple because the Stuckelberg, canonically normalized Stuckelberg, as you can see from here, enters with the inverse power of the mass. So something is going wrong with the interactions of the Stuckelberg in the limit when mass goes to 0. Okay? So now to illustrate this point, let's do the following thing. So in other words, let's add that term, okay, here. So we'll have we have this, and then we are adding this term, okay. All right, so now, and now to illustrate the point, to make a shortcut, to illustrate the point, let's take the limit, a double scaling limit, okay? So double scaling limit we can take in which gamma goes to 0, m goes to 0, okay? But we keep the ratio of gamma square over m to the 4th fixed, okay, and non-zero. All right? Okay? Now we can count very easily that in this limit, of course, this disappears, this disappears. All the terms disappear except the highest term in 1 over m. Okay? So in that limit, what happens is that the theory, in this limit, theory becomes a Maxwell plus a decoupled scalar with a self-interaction. With a self-interaction of the form okay, with a 4th order derivative self-interaction. Okay? With this finite coefficient, now this coefficient has dimensionality of the mass of the scale, right? So therefore I can call this 1 over lambda to the 4th. Now let's stare at this interaction term. Okay, so what happens? What happens here is that this is an interaction which is pretty unpleasant because it's a derivative interaction. Okay, it's a derivative self-interaction, which of course grows with momentum transfer. Okay, and becomes strong above energies lambda. So in other words, lambda is a strong coupling scale of this problem. So the lambda scale, which is m over square root of gamma. Okay, this is a strong coupling scale of the problem. This theory breaks down above that scale. So it becomes strongly interacting, violates perturbative unitarity, and therefore needs to be ultraviolet completed. Okay, so requires ultraviolet completion above the scale lambda. Right? So in other words, the question is, so can we have an interacting theory of a massive gauge field, of a massive photon, So this a consistent interacting theory, UV complete. Of course, we can have interacting theory at low energies, but UV complete. And that's precisely what Higgs effect gives us. So that's a Higgs theory. Higgs theory gives a possibility for a massive, already at the U1 level, okay? Right? For SU2 in the standard model, this is even more manifest, right? But already at U1 level, if you want to somehow have a U1 photon, massive, which can interact non-trivially somehow, exchanging with some particle exchange, etc. All right. So the Higgs model gives the possibility of that. Okay. So now, okay. So let's see this in one step. That this is indeed the case, and then we will close this circle of understanding what comes from the Higgs, what comes from unitarity, what comes from gauge redundancy. Okay. Right. So now. Let me go bottom up. Okay, let me ignore this term for this interaction term. So again, I start with so let me do again. So let me go back to the so let me go back to a dimensionless quantity. Let me call it theta. Okay. All right. And actually, in order to allow to be more general and to allow more freedom between the between a mu and theta, okay. Right. Let me call this 1 over g. Okay. Let me introduce a parameter g, which will become clear in a moment. Okay. So then I can write this down as 1 over g d mu of theta square. Okay. Now, what I need to do now is to go to ask the following question. This is Procca theory. Okay. So this is Procca, in which we wrote mass by hand. How to go from here to the Higgs? Well, one step. What you need to do is to think about this mass as a field. Okay. So in other words, you need to think about mass term as coming from the expectation value of a field. All right, so I need to simply think of m square as an expectation value of the field, which couples through the coupling constant g. Okay, and let me call this field rho. Okay, so there is a real scalar field rho. Okay, so okay. So I write this there. What else do I need to do? Since I have introduced the field, I have to give it a kinetic term. Okay, so, right? So we give a field a kinetic term. Okay, and what else? Well, I need a potential that will tell me that the expectation value of this field is non-zero. Okay, so then on top of that, we'll have a potential which will tell me that the expectation value of rho is non-zero. Let's denote it by V. Okay, this expectation value, right? Okay, so now this is the theory. Now, obviously, you will agree that rho has nothing to do with gauge redundancy. Rho is a dead singlet. It could not care less about gauge transformation. Okay, so therefore, introduction of rho could not possibly be connected with gauge redundancy. And it's not. Introduction of rho has nothing to do with gauge redundancy. The story with gauge redundancy we finished the moment we understood that there was a Stuckelberg degree of freedom which was maintaining this gauge redundancy. So rho, the Higgs field, is not adding anything to this story. Okay. Now, one more step. This theory, of course, you can see it as a model, as a Higgs model immediately. Okay. Right? Rho-Tengler Higgs and all these discussions about how to generate masses, right? Mass from the spontaneous breaking of symmetry, but we are going bottom up, right? So the only thing I need to do is to introduce a field. Let me call it capital phi. Should I call it capital phi or H? Let me call it H, just to. But H was Hamiltonian, but okay. Now it's. Now it's a field. H, which is simply rho I theta. That's it. Okay. This is this famous Higgs field. All right. Now, in this language, this Lagrangian is just you can immediately see that you can rewrite it as this Lagrangian simply. Oh, sorry. And let's put here 4. Okay, this is the famous Higgs model, right? So this is nothing but this. So in other words, the only difference between Higgs theory and Procca theory is in terms of introducing a degree of freedom, which, when it fluctuates, this degree of freedom, this is a fluctuation of the mass of a photon. Okay, so it allows the fluctuation of a mass of a photon. This is the degree of freedom. This is Higgs. Now, of course, it looks like a small difference, but it's a huge deal. Why? Because now this theory avoids this problem of unitarity violation of this type. Okay? We can see explicitly that now if I take this theory, we are finished, right? Or there is still 1 minute or something? 1 minute, yeah. Now, sorry, let me to use the space here. So the vacuum of this theory is, of course, the expectation value of rho is given by V, okay? And therefore, it's the usual story. We go near the vacuum, and we allow rho to fluctuate around the vacuum point, right? So we say now that rho is its vacuum expectation value plus a field, and this is this famous Higgs field. Okay, so now this field is massive, because as you can see very easily, this is the famous Mexican head potential, okay? And this Higgs field corresponds to the fluctuations around the vacuum, and the mass of this field is given by, okay, the mass of the, so there is mass of the photon, which is given by the mass of the photon, which from here is clear, is given by G times V, and mass of the Higgs particle, which is given by lambda times V, okay? So we just recovered this usual relation that you encounter in the standard model all the time, that the masses are set by the expectation value. Mass of the Higgs is set by its quartic coupling, and mass of the photon is set by, okay, not photon but gauge field, in the by the gauge coupling, okay? Now, for instance, we can go from here to here. I can give you this as an exercise. If it will not do it, we can do it in the next lecture in one step. So, for instance, if let's say if we can take the situation when lambda is much bigger than G, okay, for definiteness, okay. So then we have this is photon somewhere here, and then somewhere here we have a Higgs. So there is we can create a energy domain which is below the mass of the Higgs and still above mass of the photon, okay? And in this energy domain we can integrate out Higgs because it's heavy. Now it's not a ghost, it's a healthy particle, so therefore we can integrate it out. And write down an effective theory for a massive photon below this scale. Now, in this effective theory, we will, you can see it if you do this as an exercise, just do it to the leading order, okay, to the leading order in H. So if I integrate out H, integration out will result to interactions of this form. Okay? Of course, this form will be corrected by, since you are integrating out massive degree of freedom, you will see how it will get corrected, okay? But there will be interaction among the Stuckelberg fields, longitudinal component, mediated by a Higgs particle. So that's the point. In other words, what happens, roughly speaking, here, and let me finish with this, is that the interaction in case of Proca, right? This interaction that we put by hand was pathological, right? Was simply and looked like a very dangerous contact interaction of a field. But what integration out of the Higgs gives, it gives something that imitates this at low energies, but which does not suffer from ultraviolet problems. In other words, what Higgs does, as you can see, once I integrate out Higgs, I'll generate terms of this form. Now you see, the terms of this form at energies much below the Higgs mass, they look like contact interactions of this type. But this is how Higgs resolves the unitarity problem. Because in reality, this interaction is not a contact interaction. It's a result of integrating out. So in reality, this interaction is integrating out a Higgs particle. Okay, infinite series, of course, of this. Okay? Any questions so far? So then we are finished, right? Yeah. Right. Okay. Yeah, of course, that happens very often that you don't have immediately questions. But there is something that you don't like, but you don't know how to formulate the question. And then questions comes later, okay? So yeah, I'm here, so you can ask me whenever. Yeah.
How we can see that there is a quartic interaction
You mean in the Higgs model?
Yeah.
No, in the Higgs model there is no quartic contact interaction between LMU. This is the Lagrangian.
Sure, but as you see it going from your initial approach, you wrote down the quartic interaction.
By hand, yeah. Yeah.
We saw that in this limit.
There was a problem, yeah.
There was a problem. But now we recover this term.
Yeah, now you can see that you can recover this term and infinite number of all possible terms like that, infinite series, by integrating out a Higgs particle.
But still we cannot imply that there can be a quartic interaction between AB terms.
No, there is. I mean, there is. In other words, what I'm saying is, so okay, let me go through the logic again. So what was the step? What were the steps? So we said, okay, let's write down the massive theory let's deform a theory in a healthy way. We wanted to give an example of a theory when a deformation of a theory which seemingly violates gauge redundancy is healthy, and so the example is a massive photon. Now, if we deform photon by a mass, then it's healthy. Everything is healthy. It doesn't propagate ghosts, etc. Now, then we said, okay, what is the problem with this type of theory? And the question was, what about interactions? Okay, so as long as theory is free, everything is fine, obviously, right? Because there are no ghosts. But as soon as we put interaction, some trouble may happen. And we gave an example of interaction that we could write down, which was seemingly innocent, right? Because we said, okay, look, there is a 4-boson interaction with a coefficient which is dimensionless. Looks like a very nice interaction, okay? And we showed that that interaction actually is not innocent. Because, and the problem is generic, and this problem is generic illustration of, this is an illustration of a generic problem, that whenever you put interacting theory of massive gauge fields, to which mass is given without the Higgs phenomena by hand, the longitudinal components, they become strongly interacting above certain scale. This happens in the standard model with longitudinal Ws, for instance, okay? So in the standard model, what was the argument that we knew theoretically that either Higgs or some kind of ultraviolet completion should show up at LHC. It was absolutely impossible that LHC would just go through and see nothing. Because longitudinal W bosons in the standard model, they become strongly coupled above certain scale. And there is a finite window of opportunity where the new physics, this was, at the end of the day, it happened to be a Higgs, right? The simplest version. But some new physics had to come up to regulate this. Okay, so now, so we illustrated that there is a problem. And then we showed, okay, now, can I have an interacting theory which is not exhibiting this problem? An example of this interacting theory is an Higgs phenomena. And the final step was to show that if I start with the Higgs, I will generate all possible interactions like that at low energies, but those are harmless because those are regulated by the Higgs. So the Higgs resolves those interactions. They are not elementary vertices, right? So this was the logic, right? Yeah.
Yeah. So if I remember correctly, when we derive the photon propagator in QED, let's say,
yeah,
we can't invert the quadratic action because it has 0 eigenvalues. So we add precisely the term.
Yeah,
that
here
you were saying
sure.
that makes the theory like nonsense or whatever.
No, in the case of you fix the gauge. There you are fixing the gauge. There is a difference between fixing the gauge in a gauge redundant theory,
right,
and trying to deform the theory itself by seemingly violating gauge redundancy by introducing terms that are not gauge redundant. As long as the gauge fixing is just a way to make your equation invertible.
Right, but in practice we do exactly what you did, right? We add that 1/2 psi.
Yeah, but I understand. But you remember that this is not your theory. You are doing this as a technical tool for inverting equation.
Right.
So you remember that this is gauge fixing.
Right.
By the way, for instance, sometimes people like to quantizing photon, and I'm probably one among these people sometimes, to quantize a massive version, okay, and come down with it, because, for instance, for massive version, you don't need to add any gauge fixing or anything like that. If we want to write down the propagator of the massive photon, then we simply have this Proca constraint. It's just a constraint. Okay, I erased everything. But there is a constraint. So that's another possibility, to start with a massive theory, okay, quantize it, and then they take the limit properly, the limit when mass goes to 0. Remembering that the Stuckelberg is there and disintegrates. That's another way of doing it, yeah.
So what's the problem about when it's strongly coupled in this theory of
You mean here?
Yeah.
The question is, what is the problem if theory is strongly coupled? Yeah. Well, the problem is that, so at the fundamental level, so we have to distinguish between the problems of calculability. Okay, so now in analyzing the scattering amplitude, okay, usually we work in perturbation theory. Okay. Now, to work in perturbation, that's why I was insisting that good degrees of freedom are the ones that are weakly interacting, okay, right? Now, why am I insisting on weak interaction of degrees of freedom? Of course, you can always tell me, who cares? I mean, finally, even if Hamiltonian is not diagonal in some degrees of freedom, even if some interactions are strong, at the end of the day, if theory is unitary, and I have an extremely powerful computer or a powerful person that can compute everything, they can compute everything. That is true. If theory makes sense, then in that theory you can make computations even non-perturbatively, and so finally you'll get some answer. Now, here the question is, when perturbation theory breaks down, when theory is perturbative, there we feel comfortable because since we are under control using perturbation theory, we feel comfortable with we convince ourselves the theory probably makes sense, right? Although, as you know very well, the perturbative series, for instance, in terms of, they are also asymptotic series. The multiplicity of Feynman diagrams increases, and sooner or later, the multiplicity of Feynman diagrams is so high that actually overpowers any suppression by weak coupling. But anyway, this is a separate story. So yeah, in other words, when the perturbation theory works, we can calculate things, and also we feel comfortable with these calculations, obviously. Now here what happens is that for sure perturbation theory breaks down, right? Okay, so effective alpha, in other words, effective, there is no longer an expansion parameter once you go above this energy. There is no small number in which you can expand. So this means that the process with 4 phi's becomes equally important, the process with 10 phi's and so on. And so the series break down. The question then is what you do with this theory. First, how can you convince yourself that this theory still makes sense? Okay, maybe it makes sense non-perturbatively. That's a perfectly legitimate option that theory makes. But it's better to have ultraviolet completion, which is calculable, and that's what the Higgs integrating in Higgs is doing. So yeah, so that's the thing. But by the way, if you ask me, I think there are theories in which. First of all, okay, for this you don't have to ask me. For sure, there are theories like gravity, for instance. There are theories which are non-renormalizable, and we know that at least there are very good arguments that interactions of gravitons which are non-renormalizable cannot be resolved to renormalizable interactions by integrating in whatever new physics. Okay, so gravity is at least one example of a theory which is intrinsically non-renormalizable. Okay. So this means that there are theories which are intrinsically non-renormalizable, and they UV complete themselves in some other way, not in the way of integrating in some weakly coupled degrees of freedom. So yeah, absolutely.